All right. Well, we are very happy to have Grant virtually here to give the particle theory seminar this week. Grant does lots and lots of cool stuff involving quantum field theory and gravity, and especially constraints, sort of formal constraints on their behavior, with some of which he'll tell us about today. So I'm excited to hear. Take it away, Grant, whenever you're ready.
Sure. Well, thank you very much, Seth, for the invitation. It's great to be virtually at Chicago. So today I'm going to talk about how to constrain, in particular, the Standard Model EFT using Amplitudes techniques in a very general and largely UV independent way. So this talk will be based on 3 papers that I've written recently with my collaborator, Nick Rod, who is at Berkeley. So just as motivation, we've sort of entered a unique era of particle physics in the past few years. We've discovered the Higgs, but we of course haven't seen supersymmetry yet. So it's arguable we might be entering a kind of post-naturalness era for particle physics. But in a sense, model building is wide open. We might see new physics soon. We might be in, unfortunately, the desert scenario. In any case, it is very possible, perhaps even likely, that the first hints of new physics will come not from producing new on-shell states, but perhaps from precision measurement, looking for deviations from the standard model. And this can come from a lot of different avenues, including Higgs factories, high luminosity LHC, but also lower energy precision measurements like muon G-2, neutron EDM, etc. And so it behooves us to understand as best we can the standard model as an effective field theory. So within the space of EFTs, how do we build a quantum field theory? Well, we can famously, in the textbook way, write down a Lagrangian built out of some operators with some couplings, generic numbers, and just quantize it, read off the Feynman rules, calculate scattering amplitudes, etc. But if these operators are higher dimension operators, that is higher mass dimensions, so higher numbers of derivatives, for example, then this process is not guaranteed to create a consistent quantum field theory. It turns out not all couplings for higher dimension operators are permitted. That is, not all of them can show up in well-behaved UV completions, and certain whole regions of coupling space are excluded by basic infrared physics principles that we expect to be true of any healthy high energy theory. Principles like unitarity of quantum mechanics, so conservation of probability, causality of signal propagation, no time machines, or locality, or in its amplitude form, analyticity of scattering amplitudes. And in the past, past roughly decade especially, this has been used to constrain a whole litany of higher derivative terms in everything ranging from massive gravity and higher curvature gravity to applications to the A theorem in 4 dimensions. So here's just a sampling of a lot of, especially what I've been thinking about in this direction. But despite all this progress, there hasn't been a whole lot that's been done to apply IR consistency techniques to the full-blown standard model effective field theory itself. I mean, there of course has been some work done, but it hasn't been done in a completely general and fully systematic manner. But there are compelling experimental reasons for doing so. So if we imagine that this is parameter space for some standard model EFT couplings, our experimental friends will place bounds that look qualitatively like this, centered on 0. But infrared consistency comes along and cuts through an order 1 fraction of that parameter space with each bound you place going through the origin. And so it gives us a powerful theoretical prior that can enhance the statistical significance of our experimental bounds. Or said another way, were we to discover non-zero couplings in the forbidden region, that would tell us something extremely surprising about the UV. It would tell us that the UV is violating basic precepts of quantum field theory. So that itself is a good reason for looking at this. And in fact, the LHC is already in print placing bounds on higher dimension operators, dimension 6 and dimension 8 operators in the standard model EFT, without yet taking into account IR consistency. So this is a timely thing to be doing. So in this talk, we're going to apply infrared consistency, namely analyticity and causality bounds, to constrain the Standard Model EFT. We'll be thinking about 4-point operators, and we'll be looking at mass dimension 8 at first, so we want the number of momenta divisible by 4, but we'll eventually look at mass dimension 6. And for simplicity, I'm going to be looking at all fermionic or all bosonic operators, though one can, of course, consider mixed operators. So at dimension 8, so this will go like 1 over some UV scale to the 4th power. In the Standard Model EFT, there are 64 bosonic operators and 2,763 fermionic operators. And we'll place 27 and 25 different bounds, respectively, hopefully if time permits, and connect these to experimental searches. In particular, these bounds will give really interesting links between qualitatively different experiments, between LHC searches and, for example, neutron EDM or mu3e and other lower energy experiments.
Sorry, Grant, can you clarify by
Yes.
fermionic operators? I mean, you mean operators that involve fermions, or
yeah, yeah, exactly. I just mean operators that are built out of fermionic fields.
Okay, so they the definition of fermionic means they have at least 2 fermions or something like that?
Well, in this case, I'm looking at quartic operators. So I'm going to do all bosonic and all fermionic in this talk. So there'll be operators like glue glue goes to glue glue, or quark quark goes to quark quark.
Can there also be like psi psi ff?
Sure, absolutely. I mean, you can place.
Where is that in the list?
That won't be in this talk. That doesn't yet appear in the literature.
I see.
That's dimension 7, right?
Yeah, psi goes to f. Yeah, I don't think you can build a dimension 8 operator actually with.
Well, but I could do psi phi phi or something like that, right? I can use one of the use the scalar.
Sure, but that's dimension 5 then. I think you need it to be even mass dimension to even have a chance of placing one of these bounds.
So this dimension 5 operator, even though it's leading, will not be bounded.
The dimension 5 operator is not bounded, no.
Well, in the standard model, there's only one. That's the neutrino mass operator.
Right, the Weinberg operator.
Grant, is that an in principle statement or using the methods that you're going to talk about?
Well, I mean, it's hard to even imagine how one would bound an odd mass dimension operator, just because, well, I think the reasons for that will become clear once I show you how we place the bounds.
Okay.
Yeah. And typically in the literature, one has to go all the way to dimension 8 before you can even start placing bounds, again, for reasons that will become clear. But later in this talk, I'll actually show how to overcome this barrier and place bounds on the dimension 6 for fermion operators. So psi psi, psi psi. And we'll derive a bunch of independent families of bounds at dimension 6.
So the coupling to gravity plays no role in this discussion.
This will not be a gravity talk, no.
Yeah, okay.
I mean, it's definitely interesting. It'd be really cool to do sort of a GR SMEFT. So, Standard Model EFT plus gravity, and write down all of those operators and bound them. But that's not something we've done yet.
No, so I was thinking more of the swampland consistency in coupling to gravity.
Right.
Yeah,
no,
okay.
This talk will be about consistency just within quantum field theory.
Yeah, good.
Okay, so let me first briefly review how infrared consistency bounds work for a toy theory. So with a massless scalar with a shift symmetry, the first higher dimension operator one can write down is mass dimension 8. It's the d phi, the 4th operator, which is sort of the poster child for this whole program. You can compute the scattering amplitude. It goes like s squared plus t squared plus u squared. Let me instead go to forward kinematics. So t equals 0, which means in state equals out state. And when you start hearing forward kinematics, you should be thinking the optical theorem is going to come in here somewhere, which it will. So we want to extract the Wilson coefficient. So let me just analytically continue momentum in the complex S plane and do this contour integral of the forward amplitude to extract the Wilson coefficient. Then I'm going to use analyticity to deform the contour. So what analyticity is it's just the statement of locality. The laws of physics don't let you wiggle some quantum field here and have the field instantaneously wiggle in Andromeda. So that means the laws of nature are of finite order in derivatives, which in momentum space means we should expect Taylor series in momenta, or in complex momentum space, we should expect analytic scattering amplitudes, except for branch cuts or poles associated with on-shell production of massive states. So the boundary term at infinity will vanish under fairly general assumptions. And crossing symmetry allows us to rewrite the integral over the negative s-axis as an integral over the positive s-axis. I'm going through this quickly because this is all pretty standard. Ultimately, what we get is that this Wilson coefficient can be written as an integral over the imaginary part of the forward amplitude over the real positive s-axis. But by the optical theorem, the imaginary part of the forward amplitude is positive. It's just a cross section. So the Wilson coefficient is really just encoding some integral of the cross section of these two phi's going to anything integrated over the UV. So it's by definition positive by unitarity. So we're going to apply this same idea first to bound the dimensionate four-fermion operators. So I want to build all 4-point fermion operators that have 2 extra derivatives by dimension counting to get to dimension 8. So the counting for this can be found in this paper by Henning et al., but the operators themselves aren't there, and they weren't in the literature at all until fairly recently. So we had to construct them ourselves, but that's okay. The ingredients are just standard model fermions, the quarks and leptons. And each of these fields will write with a generation index running from 1 to NF, where in the standard model NF is 3. And so this will define our flavor quantum numbers, like strong isospin, charm, etc. And since we're going to consider scattering of states of fixed standard model representation, so like not a superposition of a quark and a lepton, we'll require operators that contain an even number of each fermionic field modulo flavor. So we have to mod out by all the Fiertz and Schouten identities, mod out by equations of motion, etc. But we can do this, and we get the following basis of operators. So we get operators that look like DJ, where J is just some kind of a current. So psi bar, gamma mu psi, maybe with some SU2 or SU3 generator crammed in there. So these are the self-quartics. Now the cross-quartics, we again can have DJ squared type of operators. But in addition, there's a different kind of cross-quartic, which sort of looks like T mu nu squared. It's like psi bar d psi bar d psi in a way that can't be rearranged to be equivalent to one of the DJ squared operators. So we'll bound these two. And we'll write the Wilson coefficients, as you can see, as A, B, and C. And they're 4 index tensors running over the flavor indices. So what the positivity bounds will give us are structures in flavor space. So for now, we get to ignore dimension 5 and dimension 7 operators, as well as the standard model scattering contribution. Of course, dimension 6 operators can be present, but they can only generate s-squared amplitudes via loop processes, so we can ignore them, assuming a sufficiently weakly coupled UV completion. So let's skip to what bounds we actually get at dimension 8. So we're first going to scatter right-handed leptons. These are the simple ones, the ones that are standard model singlets. We'll scatter right-handed leptons in an arbitrary superposition of flavors. So alpha, beta, gamma, delta will just be the wave function coefficients telling us what superposition of flavors we're scattering. And when we compute the forward scattering amplitude, so E plus E minus scattering with the in state superposition of flavors equal to the out state, we get this structure. So our Wilson coefficient tensor dotted into our wave function coefficients times s squared, as we expect. So unitarity and analyticity require that C MNPQ dotted into alpha, beta, beta star, alpha star must be positive for all possible vectors alpha and beta. So before we move on to all the other operators, let's think qualitatively about what this is telling us. We can think of these outer products for alpha and beta as matrices that are automatically idempotent, Hermitian, and with unit trace. So the rows are really just density matrices for a pure state on a Hilbert space of dimension NF. where the alpha alpha star is just the Schmidt decomposition. So we can write this as some function over all density matrices labeled by alpha and beta. So what we're requiring is that C alpha beta is positive. So let's explore this in a simpler theory than the full standard model. So consider a toy theory with just two flavors. Suppose it's CP conserving, so all the Wilson coefficients are real. And let's define C, C0, C1, and C2. So C2 breaks flavor by 2 units, C1 breaks the flavor symmetry by 1 unit, and C0 will be the Wilson coefficient conserving flavor symmetry. And then let me define X0, X1, X2 as the ratios shown here. So then our bound just becomes these statements. So it's not just a simple positivity bound. We end up requiring that the Wilson coefficients live in this essentially in a particular kind of cone in flavor space. And so here's a visualization of that. And what this tells you, since X1 and X2 have magnitudes that are bounded, this tells you that the flavor violating operators are forbidden from being too large compared to the flavor conserving operators. So that's really interesting, and that's qualitatively different than what we found just from the d5 to the 4 example, where it was a simple positivity statement. Right. So the same sort of thing happens for L to the 4 operators, except that now we get to scatter not only superpositions of generations, but also superpositions of the SU2 left charges. So we have to mod over all different directions in the SU2 charge space. And when we do, we marginalize over the angle between the two wave function vectors, and we get 2 independent bounds on the L to the 4th operators, as you'd expect. But it's still of the same qualitative sort of bound as we found for the E to the 4th case, in that this will still bound the flavor violating operators. It will bound them in magnitude from above in terms of their flavor conserving cousins. So the same sort of thing happens with the quarks. We get a bunch of different families of bounds by marginalizing over all the different directions in SU2 and SU3 space. And again, the same sort of thing happens with the cross quartics. So as I said, some of our operators conserve flavor and others are flavor violating. So for example, this operator here, 1 bar 3, 3 bar 1, obviously conserves flavor. But this operator, 1 bar 2, 3 bar 1, violates violates muon number and tau number by 1 unit. So our bounds imply positivity of various flavor conserving coefficients, like these operators here. And these correspond to diagonal density matrices. But more generally, we get bounds of this sort from the off-diagonal elements of the density matrices, where some flavor violating operator like this one that violates muon and tau number by 1 unit will have magnitude upper bounded by a product of the analogous flavor conserving operators. Any questions so far?
So yeah, sorry, go ahead. Oh, sorry.
Go ahead, Simon. Go ahead.
Yeah, I'm just trying to understand, like, if I say turn off a flavor conserving operator and then try to see, like, if I do the scattering, of course, looks like I don't have a forward scattering at all. So basically, the fact that you're assuming there is a forward scattering to begin with requires that there is a flavor conserving operators, and then you're bounding how much violation you can get by saying that. I'm just trying to understand, like, how analyticity and then unitarity actually can affect on the symmetry space.
Right. So, okay. So the idea here is, imagine that you're scattering some superposition of different flavors. So like a superposition of electron and muon, right? Yeah. So let's say I scatter a superposition of an electron and muon off of an electron, okay? And if I go to forward scattering, that means I'll get superposition, an electron goes to superposition, and electron in the forward limit. So that will be sensitive to operators that violate electron and muon number, but also ones that don't.
Right.
And it is not consistent to just turn off the operators that don't violate flavor, in the same way that it is not consistent to turn off the d phi to the 4 operator. The d phi to the 4 operator is provably positive, strictly positive.
Right.
Because if it were 0, that would mean that the integral of the cross section would have to vanish. So the only way that it can be 0 is if you're in a free theory.
Right.
So so yeah, we're indeed saying you can't just turn off the flavor conserving operators, which is why we get positivity bounds for those. But then what we're also saying is that if you turn on the flavor conserving operator and also the flavor violating operator, if you make the flavor violating operator too big, then it is possible to choose a superposition,
Right.
such that you would be forced to conclude that the cross section is negative for scattering with that superposition.
Okay.
If our bounds were violated.
I see.
So it would be exactly like having a negative d phi to the 4. There's some superposition for which the effective like d phi to the 4 type of operator would be negative.
Okay.
Grant, I'm confused about something you said in your answer. I think I'm not understanding the assumptions well. So it's certainly the case that there exist scalar theories that have interactions where there's other fields involved that have no d phi to the 4th coefficient in the Lagrangian.
Well, like the special Galilean, for example, the d phi to the 4th operator is forbidden by a symmetry, right?
Well, how about something simpler like, some Yang-Mills theory with some interacting gluons and scalars? There's no d phi to the 4th there. And so there's no way to prove that the d phi to the 4th interaction is non-zero, because it's just 0 in those theories.
But okay, in those theories, then what does the s squared coefficient of the forward amplitude for elastic phi scattering look like? If the coefficient of s squared in the phi amplitude vanishes, I claim that that's a sick theory. Because
I mean, we're not talking about anything exotic. Let's talk about like n equals 4, or, some theory that we all agree upon as being totally fine.
Okay.
There are scalars, they interact. Their cross sections are not those of the free theory. Their amplitudes are not those of the free theory, and there's no d phi to the 4th term in that. Right? So it's more a question for you. I'm trying to understand. You said that you could prove that term is non-zero, but I think there must be additional assumptions that I'm not understanding.
Right.
I mean, so
this is a cutoff, right? So you need to integrate out some modes, right? And then, sorry, I should have let Grant.
No, I mean, so okay. It is possible for there to be no fundamental d phi to the 4th term, certainly. I mean, like, in a nonlinear sigma model, for example, I could have some massive sigma coupled to d phi squared, right? Then there's no like real d phi to the 4th term. But nonetheless, if sigma is massive, then at low energies, I get an effective d phi to the 4th term. All I'm saying is that if you, at sufficiently low energies, there should be an effective theory of the scalar in which there is a non-zero d phi to the 4th term, non-zero Wilson coefficient for d phi to the 4th. If there is not, and if the amplitude is analytic, and if there are no other subtleties like strange issues with like poles in the forward limit or something like that, then indeed the d phi to the 4 Wilson coefficient must be positive, or else you either violate analyticity or have a free theory.
Wouldn't it be that all of this bound must come with equality sign as well? It just, in that sense, of course, but you're basically turning off all of the.
Well, yeah, but in the case if you in the d phi to the 4 example, since you can write the coefficient of d phi to the 4 as an integral of the cross section,
right?
that means it either has to be strictly positive or else you have a free theory.
Right. So it can include equality.
It can equal 0 only in the case of a free theory. So a non-free theory in which this equals 0. So for example, a Galilean theory marginally violates this positivity bound.
Well, it may just be that the force scattering that you're looking at just do not occur just because of that channel is not allowed. That's all. But the theory can be interacted.
Right. That channel can be not allowed.
Sure. Right. Okay.
But not allowing means it's a free theory.
Right. Not allowing. Yeah, exactly. It means those degrees of freedom are free. Yeah.
So what is the resolution when there's just no explicit d phi to the fourth term in the Lagrangian? I'm a bit.
He's claiming
there doesn't have to be an explicit d phi of the 4. All I'm saying is that in the fundamental theory, there's not going to be an explicit d phi of the 4. It's just in an effective description of the theory at low energies, there must be a non-zero d phi of the 4, or else you've shown me a free theory.
So the claim would be if you took n equals 4, you took the continuum theory and integrated out any tiny amount of UV modes, it would generate that operator with the right sign, right?
Right.
Yeah. Okay.
It has to generate that operator.
Right.
Yeah.
So that is the assumption. The assumption is that you've perhaps the assumption that Clay was looking for is that there are some modes that have been integrated out, right?
Right. Yeah. Of course.
Yeah. Okay. Good. Clay,
Doesn't that mean that that all of these amplitudes that we're discussing get contributions not just from the explicit terms higher in the Lagrangian, but also from the interactions from the lower dimensional terms? That's what the matching calculation that Seth just suggested would.
Well, yeah, but what you're describing there is just well, RG evolution in effect.
No, I think you're missing my point. My point is that if you don't take that into account, if the amplitude depends on that you're bounding depends on both the coefficient of the higher derivative operator and the interactions from the lower derivative operators, then I don't understand how you're going to get just so clean bounds on just the higher derivative coefficients.
No, okay, but as I've said, none of the higher derivative coefficients are fundamental higher derivative terms. One always imagines that these higher derivative operators are generated by integrating out some massive states that couple to, for example, phi, through lower dimension operators, like sigma d phi squared in the example I gave. One does not imagine.
The example that we were talking about, we had some gauge theory, and it was defined. It was a UV complete theory. We lowered the cutoff. We generated some higher dimensional terms. Now,
sure.
Those higher dimensional terms, do we have bounds just on the coefficients of them, or do these bounds also depend on the interactions from the lower dimensional terms that are still present?
From yet lower dimension?
Like it's not like I'm just going to get free plus the only interactions are higher dimensions. In general, there will be interactions among the lower dimensional terms as well. Right? In general, it's not just a free theory, and then the first interactions are these higher derivative corrections.
But even you have other interactions. I think he's claiming that this dimension 8 operator is strictly positive if d phi, if phi interacts at all.
Yeah, so that's the thing I'm trying to understand, how that escaped depending on the interactions from the lower dimension operators.
So do these interactions among lower dimension operators generate a contribution to the forward amplitude that goes like s squared?
Well, for instance, in the example where we discussed where we took any unitary theory involving scalars and integrated out a little momentum shell, the answer must be yes.
Right. So then, so the claim is then, if you compute.
All right, sorry, no, lower dimensional term does not contribute to s squared at the low energies.
Right, just by dimensional counting, I guess. If you need to have 1 over lambda to the some power to get s squared type of behavior.
Well, right. I was assuming Clay was imagining multiple insertions of one of these lower dimension operators.
Yeah, multiple insertions, loops, whatever. Yeah,
3,000 insertions won't get you s squared. There's
right,
just no dimensional analysis.
Right. There's no 1 over lambda, no matter how many factors of lower dimension operator you insert.
Sorry, if you lower the momentum shell, you generate it by the lower dimensional.
Let's think about the integrating out physical scales, right? Integrating out particles, right? So this is a, yes, if you want to think about that way, yes, you already generate higher dimensional operator. He's claiming the leading in this way, you are just adding to that the d phi to the fourth operator, contributing to the S squared.
Yeah,
for phi, for as long as you are considering phi to phi forward scattering.
Right, which doesn't that mean that the lower dimension interactions generated that? If I do it by matching the
you're just saying RGE, this renormalizes
exactly,
that,
yeah.
That's fine.
All of these higher dimension operators are always generated by some lower mass dimension interaction coupled to some modes that you integrate out.
Yeah, he's just saying that suppose I have a theory, right? I have a I have a shift symmetry as a low energy, has nothing to do. I don't ask about the high energies, right? So what limit you can set on that dimension 8 operator?
So I think
doesn't matter where it's coming from.
Yeah,
right,
but what I'm trying to understand, and I still don't get it, is why there is a limit on that coefficient that is independent of any details of what the lower dimension operators are.
Right. So Clay,
that's a dispersion relation.
Right. The statement is that Clay, if you look at the 2-to-2 scattering, you can draw like a lot of different diagrams and there are a lot of loop diagrams, whatever. But then Grant is looking at the cross section, which behaves like an S square, which is necessarily coming from higher dimensional operator. And then the lower dimensional operator or marginal would not contribute that piece. And then he's asking, okay, this must be positive. And therefore he's getting constrained only on the higher dimensional operators.
Right, and any term in the forward amplitude that does not scale as S squared gets killed in the dispersion relation just by the residue theorem. So,
right.
Okay, I don't want to hold you up too much. Let's keep going.
Right, and I should add, in any explicit UV example, this will automatically be true. Like the effective coefficient of d phi the 4 that one finds at low energies after integrating out whatever states you like in a healthy UV theory will always just look like the square of some coupling or the sum of squares of a bunch of couplings. But yeah, okay, maybe we can move on. I should add that this claim about the d phi to the 4 theory is certainly not unique to us. This goes back to the famous paper of Arkani Hamed and friends from 2006, the IR obstruction to UV completion paper. So we're applying that technology that they used for those toy theories to these four-fermi operators. Anyway, good. So one can show also that the only possible CP violating four-fermion operators are also flavor violating. So our flavor bound also constrains CP violation. So let's look at a couple, or at an example of a UV completion. So if we have some 2 Lorentz index standard model singlet fields coupled to one of these DJ operators, then integrating out phi mu nu indeed gives us a Wilson coefficient tensor that is manifestly positive. So well-defined UV completion of this sort would be the KK graviton, which couples to T mu nu. And so it generates this tensor of Wilson coefficients shown here. And indeed, dotting this into arbitrary rho alpha and rho beta density matrices gives us something manifestly positive as required by our bounds. Right, so before I talk about mass dimension 6, I'll mention a few phenomenological consequences of the dimension 8 bounds. So there are precision experiments that are currently searching for flavor violation. So for example, muon to electron conversion, muon goes to 3 electrons. And in the mu3e experiment, if the mu3e experiment were to find non-zero branching fraction for mu goes to 3e, our bound would imply non-zero analogs among the flavor conserving operators for 2 muon to electron or 4 electrons. Which could be tested at colliders in the dilepton distribution. So this would be really cool. If you found non-zero flavor violation, you'd immediately have a prediction for some flavor conserving operator that you could see in a totally different experiment, just as a result of basic principles like analyticity and unitarity. Now, of course, there are dimension 6 analogs of all of our operators, but these can be discriminated from dimension 8 by, for example, looking at the higher L angular distribution or looking at the high PT tail, and you can tell them apart in that way. So I should also mention that the scaling, the fact that the dimension 8 operators scale more quickly with momentum means that sometimes it's better to look at the branching fraction of operators that aren't as highly constrained, but where you win by virtue of the mass ratio. So for example, tau goes to 3e. So there are other probes that I won't have time to talk about. But in the second part of my talk here, I want to mention how we can get over a theoretical barrier to extending bounds of this sort to dimension 6 operators. So as I mentioned, traditional dispersion relations require bounding operators with at least 4 powers of momenta, so mass dimension bigger than or equal to 8, because in the forward limit, you're bounding the s squared or s to the 4th or s to the 6th part of the forward amplitude. But of course, as we know, the standard model EFT starts at lower mass dimension. There's one mass dimension 5 operator, the Weinberg operator, but things start getting really interesting at dimension 6 in the basis enumerated in this famous Warsaw basis paper. So it'd be nice to bound dimension 6 operators. For example, the 4 fermion operators, psi to the 4th. But these have amplitudes that go like momentum squared, so like st and u. As we know, the optical theorem applies in the forward limit. So as t goes to 0, the amplitude would either vanish or it would flip sign under crossing symmetry, leading to a sign ambiguity in the dispersion relation. And this obstructs a straightforward application of positivity bounds. So how can we get around this? Well, let's start with some rules. For concreteness, consider the 4 electron operator. And we'll choose flavor superpositions to correspond to forward scattering as before. And we'll consider scattering opposite helicity states. So we get the following amplitude in spinor helicity variables. We get, again, the same sort of structure we had before, times something that will go like S or T. And let's just see what we get from a forward dispersion relation. So we run through the same kind of argument. And what one gets is a dispersion relation with a sign ambiguity, as we predicted. The s squared instead of s cubed in the denominator results in a relative sign flip between the two integrals. So this is positive, but this is manifestly negative. And what's sort of interesting is this is exactly the sort of issue that prevents one from proving the A theorem at dimension 6, in 6 space-time dimensions. You get exactly this sort of mixed sign dispersion relation. But of course, this is still useful. Instead of a positivity bound, it's a sum rule. And under various assumptions about the UV, for example, if sigma alpha beta or sigma alpha bar beta vanish for some choice of incoming states, one can get some positivity or negativity bound. So this is very phenomenologically interesting, and people have indeed wrote some beautiful papers deriving these sum rules. But we would like to do more. And what we can do is use more information about the scattering itself. So using partial waves, one can show that not only is the imaginary part of the forward amplitude positive, but all of its t derivatives are positive as you take the forward limit. And this just comes from the fact that all the Legendre polynomials, in addition to passing through 1 when cosine theta equals 1, they all have positive derivative. All of their derivatives, in fact, are positive in the forward limit. And in fact, this technology was sort of expanded maximally in the recent EFThedron paper. So in a sense, this is what we'll be using is one slice of the EFThedron. So what if we consider the contour interval 0t? So let's just extract the value of the amplitude itself at non-zero t. And we again get a sort of dispersion relation. We have some another boundary term at infinity. But if the amplitude diverges more slowly than p squared at large momentum, then you can show that, that this boundary term will vanish. And if we take the t derivative of both sides, hoping to use this relation, we unfortunately again find an integrand with a sign ambiguity. There's a minus sign here. So what can we do? Well, what we can do is look more closely at the partial wave expansion. So for scattering of opposite helicity states, so alpha and beta will correspond to opposite helicity states, which means alpha bar and beta correspond to same helicity states. Then the initial total angular momentum is 0, and the partial wave expansion is just done the usual way in terms of the Legendre polynomials. But for the alpha beta amplitude, the initial total angular momentum is 1. And that means the S wave doesn't contribute to the expansion, just in the same way that you get no monopole radiation from a photon. And what this means is that the partial wave expansion is not done using Legendres. The correct way to do the partial wave expansion is the so-called Jacob-Wick expansion into final states of definite total angular momentum using the Wigner small d matrices. And these are not the same as Legendre polynomials. Instead, they're written, in this case, in terms of Jacobi polynomials here. And these differ crucially from Legendres. So the solid curves here are Legendre, the dashed are the Jacobi polynomials, and these differences, which become fairly small in the forward limit, will be crucial. They'll allow us to rearrange that dispersion relation with an ambiguous sign into something that is manifestly causative. So let's do that. So if we expand out our dispersion relation in partial waves, we get this second line here. And if you look at the functions of J, you see that they're all manifestly positive, and they're multiplied by just the imaginary parts of the partial waves, which are also manifestly positive by unitarity. So we get a new positivity bound that we've derived. You take the t derivative of the s equals 0 amplitude minus the s derivative of the t equals 0 amplitude, and you get that it's positive. And we've used only two assumptions. One is that the UV physics is Lorentz invariant, unitary, and local. And the other assumption is that in the deep UV, we want the amplitudes to diverge more weakly with large momentum than in the IR EFT, which is a fairly minimal requirement. If you want the UV completion to be a UV completion, what that means is you want perturbative unitarity to be improved by integrating in heavy states. This is, for example, the motivation for including the Higgs boson in the standard model. If you compute longitudinal WW scattering, the amplitude momentum squared, which means they get too large around the weak scale. So you integrate in the Higgs, and then you find that at large momenta, they scale as momentum to the 0, which is nice. So there are various arguments I won't have time to get into for how we can get rid of standard model singularities, but I want to skip to what bounds we actually get for dimension 6 operators. So if we apply our bound to the e to the 4 operator here, again, we have to choose opposite helicity states. We use the standard analytic continuation of the spinors, and we get a very simple structure that looks similar to what we found before. It's the Wilson coefficient tensor dotted into alpha, beta, beta star, alpha. And if we go to the case of a single fermion, in which case we lose all the interesting flavor space structure, this agrees with the bound derived for a single fermion in this paper of Adams, Jenkins, and O'Connell, but which was derived using much stronger assumptions than we use. So we can add isospin and do the same thing for the L to the 4 operators, and we get the same sort of bounds. We can define some new Wilson coefficient tensors, B plus or minus, and we can write these bounds extremely compactly. And so we're now ready to apply our bounds to the full dimension 6 standard model EFT. So if you read off from the Warsaw basis paper, you have the following operators. You have some self quartics, and you have some cross quartics. It's not important what they all are. This is just to give you a sense of what the basis looks like. And we get a bunch of bounds that we can then go and use and apply phenomenologically. And I should add, this is the first time that model independent bounds like this have been derived for the leading matter deviations from the standard model, just purely using the analytic structure of scattering amplitudes without any additional input. So a good thing to do is to test these bounds using well-defined UV completions. So let's come up with a UV completion of the four Fermi operators in the standard model EFT. So how about a massive Higgs? So some massive scalar phi with a massive Yukawa interaction coupled to chi bar L. So chi bar will be some massive fermion. So we're going to integrate out both phi and chi at one loop. So we do that, and we find that our Wilson coefficient tensor BMNPQ is indeed manifestly positive when you contract it with arbitrary alpha and beta superpositions. So our bounds are satisfied. Another example is just a tree level with a massive Higgs coupled to E bar L. So now we'll check the cross quartic. Integrating out the massive states, again, we get our bounds are manifestly satisfied. Similarly, with a color bifundamental Higgs, we again get manifest satisfaction of our bounds. So what about massive vectors? Should we couple a massive vector to, for example, L bar gamma mu L, one finds that our bounds are not manifestly satisfied. But this is not surprising, because massive higher spin states have additional powers of momenta in their propagators. And in this case, that means the amplitude still scales like momentum squared in the UV. This means in our dispersion relations, massive vectors, or yet higher spin states, will give you poles at infinity when you do the contour integration. And so in a sense, this is really not a nice UV completion of this operator, because it doesn't improve the high energy behavior of the amplitude. Perturbative unitarity still fails just as badly in the full theory here as it does in the naive EFT. So what are some phenomenological consequences at dimension 6? Well, again, we get this nice structure in flavor space where flavor violating operators have magnitudes upper bounded by products of their flavor conserving cousins. So this gives us some interesting prospects for detection. If we write the flavor violating scale as lambda tilde and the flavor conserving scale as lambda, our bounds imply generically that lambda has to be less than lambda tilde. And in the mu3e experiment, this means if mu3e were to see a violation of flavor symmetry coming from dimension 6 operators, this would imply that lambda tilde has to be between 8 and 800 TeV, which is unfortunately out of the range of anything near term. But what about tau decay? Well, the Bell 2 experiment at super KEKB aims to improve the branching fraction of tau to 3 mu by a couple orders of magnitude, which means that were this seen, it would imply lambda tilde of around 25 TeV, which means that there would be lambda less than 25 TeV. So flavor conserving interactions that could be seen near term, fairly near term at least. Indeed, LHC bounds on flavor and CP conserving terms already put lambda above 1 to 2 TeV. So it's within about an order of magnitude of really sharply testing our bound. That is to say, near-term detection of flavor violation in tau decay would imply fairly near-term flavor conserving physics at colliders in the 10 TeV range. So I won't have really time to talk too much about bosons. Let me skip ahead here and just sort of tell you the upshot. I should add for Clay that in addition to the analyticity bound, one can get positivity of d phi the 4, at least the weak version of positivity of d phi the 4 from causality, where one puts down a couple bubbles of condensate, boosts them past each other, and you end up violating causality if C is strictly negative. Of course, in this case, C equals 0 is still okay. So for operators of the form, let me see if I can show you them. Operators of the form F mu nu squared times, G mu nu squared, we can place positivity bounds. So, photon squared, gluon squared, and that sort of thing. And we get, what's really interesting is that even for the bosons, we get the same sort of structures. we get positivity of CP even terms, and we get magnitude bounds on CP odd terms, where one of the four field strengths has an epsilon tensor in it. And it's exactly the same kind of thing that we found in flavor space for the fermions. And you might wonder why this is true. And I can kind of give you some motivation for that. So again, we find these cone type of bounds for the bosons, where the CP violating terms have to be within this allowed cone bounded by the size of the CP conserving operators. And you can sort of understand the reason by looking at example UV completions. So what these bounds mean is that we have to be able to arrange the Lagrangian here for the B mu nu operators into a sum of perfect squares. It has to be possible to arrange the action into a sum of perfect squares, which means that you can simply understand where these operators are coming from by integrating in, for example, a dilaton and an axion with mass mixing, where here turning on mass mixing turns on the CP violation. And the one other thing I want to add is that similar kinds of phenomenological consequences obtain for the bosons. So for example, let me just skip ahead here. This program can motivate new places to look for constraints that the LHC is placing. So for example, these are some CMS 95% confidence level bounds, and our bounds cut half of this space out and only allow half it. But here's another set of bounds one could place on 4 boson interactions that is accessible with LHC data, but where the analysis just hasn't yet been done. So our bounds can motivate new places to look. And we can connect CP odd and CP even operators. So for example, if a non-zero neutron EDM were discovered coming from a dimension 8 operator, then this would imply that the scale of new physics is in the hundreds of GeV, which would mean that you could probe the CP conserving cousins of these operators, like glue to the 4th, with the LHC. So just to wrap up, so some future directions, there's a lot of different potential avenues for future work. We want to think about more connections between CP even and CP odd measurements, superpositions of standard model representations, for example, to probe baryon and lepton number violating operators. We'd also like to derive standard model EFT bounds for operators that contain both fermionic and bosonic fields. It would be also interesting to think about other EFTs and indeed connections to the swampland program. And we'd also like to continue thinking about beyond positivity techniques, employing the full technology of the EFT hedron, and deriving some rules at dimension 6 beyond the 4 Fermi operators that I talked about today. And we're currently working on that. But the takeaway is that, you know, connecting in the infrared consistency program with the standard model EFT gives us a new bridge between phenomenology and formal theory. It allows us to connect physics at different energy scales and indeed even in qualitatively different experiments, and allows us to test fundamental properties of QFT up to very high energies, and thereby allows us to sharpen our search for new physics. So in the last couple of minutes, I'd be happy to take any questions, and thanks again.
Great. Thank you so much, Grant. Let me clap for everyone, as is traditional. Wonderful. Yeah, are there any questions? Feel free to unmute yourselves. Yeah, Nikita, I think you could.
Are we going to have a chat after this, or are we going
Yeah, that'd be great.
I'm asking the organizers, so I don't know.
Yes, that would be great. Yes, we have Grant. Thankfully, does have some time after this, so we'll have some extended discussion. Nikita, do you want to?
Yeah. Thank you for a nice talk. I have a couple of questions. So one is, so you've shown bounds, upper bounds on flavor violating Wilson coefficients from flavor conserving one. So I was wondering whether you can, if there's any sort of scattering process you can study to derive bounds in the opposite direction. So if you have some bound on flavor violating operators, you can translate that and turn into a bound on flavor conserving ones, or is that impossible?
Well, yeah, okay. So there's a couple different ways I could interpret that question. So I'll try and answer both. So our bounds come in two types. Indeed, we do find magnitude bounds, upper bounds on the magnitude of CP and flavor violating operators in terms of flavor conserving operators. But we also find just straight up positivity bounds on flavor and CP conserving operators. So we can say that, you know, the various flavor conserving operators are positive. But in fact, you know, if one observed a non-zero flavor violating operator in some experiment, then one would have, by virtue of our bounds, a lower bound on the size of the analogous flavor conserving operator. And that's, I think, the most exciting direction experimentally. But no, we in general, from a theoretical perspective, we don't have lower bounds, absolute lower bounds on the size of flavor conserving operators, except that they must be larger than their flavor violating counterparts. You know, it's possible for the flavor violating counterparts to vanish, in which case the flavor conserving operators can be as small as you like.
Right. So, I'm probably just missed this, but so where does this information about flavor come from? Because in principle, the only thing that tells you anything about it in the standard model is the Yukawa matrices. So if you set those to 0, there shouldn't be any distinction between the flavors in the first place.
So right, so you're saying let's set Yukawa to 0, so flavor is a global symmetry, right?
That's right.
But you can choose to scatter arbitrary superpositions of flavor.
Mm-hmm.
And then some of these higher dimension operators will have Wilson coefficients that violate flavor or that conserve it. So for example, if I have the four-fermion operator E bar E mu bar E, that violates electron and muon number by plus or minus 1 unit respectively. And if that Wilson coefficient is non-zero, we show that it's not possible to have that Wilson coefficient be non-zero without also having the e to the fourth and the e squared mu squared operator also be non-zero.
I see. Thank you.
Yeah, but by the way, can I just get some clarification of when you say you can choose to scatter linear combination of different flavors? I mean, that would naively seem to mean to me that there's a mass eigenstate, which is admixture of different flavors, so that you can define asymptotic state. Wouldn't that already mean that somehow you have in the zeroth order, almost the free theory level, you have already some sort of a flavor violation built in that assumption?
Good question. So how the standard model EFT works is it's written in the unbroken basis.
Mm-hmm.
So effectively, all the fermions are treated as massless.
Right.
So,
but then in unbroken phase, then the only sensible mass eigenstate are individual flavor eigenstate rather than like admixture.
No. I mean, if they're all massless, then
I see what. I see.
Then flavor is just a global symmetry, and in the pure
I got
SMs.
you. Right. I got you. Because there is no even notion of like diagonalizing mass, nothing like this. Massless.
Exactly. Yeah. Any vector is a mass eigenstate in that case.
I see what you're saying. Okay. I see what you're saying.
I mean, certainly one could redo this whole analysis instead of the SMEFT, you could go to, there are various other effective theories in the broken phase, the heft and left and all these others. So that analysis would be cool to do as well. That hasn't been done, but yeah, one could do this in the broken phase.
Right. Another not related question, but question is, in the dispersion relation analysis, like really from a very first version or original version back in 1960, whatever, or 50, you for example have to place some sort of singularity structure in the complex plane, and then you apply your analysis with some assumption about the UV behavior of the amplitude. So in this analysis, probably I just missed your statement, but is there any way you can determine the singularity structure in the complex plane, or you kind of make an assumption and then you apply the dispersion relation?
So this analysis uses, for the structure in the complex plane, we're using the standard S matrix assumption that all the singularities occur either as branch cuts or poles along the real S axis associated with on-shell production of single or multi-particle states.
Okay, I see. Because okay.
Right. That's input for our analysis.
Right.
Grant, this is kind of related. I think my confusion can be boiled down to also a question about the dispersion relation. Is a question of where do you need to know the amplitude and what regime of S in order to apply the dispersion relation?
Just near S equals 0.
Just near S equals 0.
Yeah. One just needs the explicit form of the amplitude in order to extract the Wilson coefficient. So if the amplitude looks like, CS squared at low energies in the forward limit, which it does in the theory of, d phi squared plus C d phi to the fourth. So given that, and assuming, without assuming the particular functional form of the amplitude, just assuming that it obeys the usual analyticity properties in the UV, and assuming it obeys the optical theorem, then you can write the low energy Wilson coefficient as this integral over the cross section. Because it wouldn't be interesting if you had to know the functional form of the amplitude in the UV. Like if you know that, you know the UV completion. And
right. I mean, of course, here we are I don't know, not a lot, but at least we are putting partial information about the UV thing by saying that it's completely analytic. So when you deform the contour from the circle to that, basically you don't encounter any other structure, right? That's
right.
One of...
Well, yeah. That in particular, the only structure you encounter are these poles or branch cuts along the real S axis, which are what give you the
right, exactly,
the cross section in the first place. Yeah. So there are certainly assumptions about the UV that it has this nice analyticity structure and that it obeys unitarity, so you can apply the optical theorem. But yeah.
Okay.